So we'll start the webinar now. Good morning and good afternoon, everyone. Welcome to today's webinar to kick off the first ICOS OTC pCO2 instrument intercomparison exercise, which will take place at the Flanders Marine Institute in Ostend, Belgium, starting next week. Arthur Palic and I will be moderating this event. Arthur is an IOCCP project officer, and I'm a member of IOCCP Scientific Steering Group responsible for instruments and sensors. We will start the webinar with a welcoming word from Werner Kutsch, Director General of ICOS, and Richard Saunders, ICOS OTC Director. Later, Arne Körtzinger and Sabine will give us a historic perspective on the pCO2 intercomparison exercises and the lesson learned from them. We'll have a short Q&A session after these introductory talks. And finally, Toby Steinhoff will give us an overview of the upcoming intercomparison exercise and the proposed activities, and will introduce the team. After the last presentation, we'll have a larger Q&A session and a discussion, and we encourage you to type questions in the question box throughout the webinar. And now Arthur will discuss some housekeeping items before we proceed.
Yes, so thanks, Tasha, and welcome everyone. Just a few housekeeping announcements. This webinar is being recorded, and the recording will be made available online sometime after the webinar, so you will receive more information about that soon. If you have any questions or comments to the presenters or us as the organizers during the webinar, please type them into the questions box. Depending on whether you're connecting through the web app or a standalone GoToWebinar application, the window might look a little bit different, but there should be this question box there. Please be as brief as possible. We will try to answer as many questions as possible during this live Q&A or by writing through the questions box. So thank you.
Yeah, so before I introduce our first speaker, I'd like to remind everyone that this webinar is the first in a series of 3 webinars. The second webinar will take place on Monday, July 12th at the same time, and it will provide a summary of the intercomparison exercise and its outcomes. The date for the final webinar to be confirmed later, but it will take place somewhere in October. And it will deliver a synthesis of the results and will give us an opportunity to discuss the results with the community before the final report publication. And now, without further delay, I would like to introduce Werner Kutsch, Director General of ICOS, with a welcoming message.
Hello and greetings from Helsinki. My name is Werner Kutsch. I'm the Director General of ICOS, the Integrated Carbon Observation System, and I want to welcome you to this pCO2 sensor intercomparison workshop. You may have heard that earlier this week there was the Show Your Stripes Day, and this was not about the stripes of a zebra. This was about the stripes that are symbolizing the change in temperature or the change in the CO2 concentration of the atmosphere over the last years, decades, or even centuries. So what you are seeing behind me is the ICOS stripes. It has been provided by Michel Ramonet from the ICOS Atmospheric Thematic Centre and compiles the long-term observations of CO2 concentration in the atmosphere over partly decades in the different stations. So, and you can see clearly in this graph, like you can also see in many other graphs, that there has been a huge change in the CO2 atmospheric concentrations, which also, of course, has changed the radiative forcing and the temperature. We know that the oceans play a big part in the global carbon cycle. There is a strong flux of CO2 between the oceans and the atmosphere. In some regions it's a flux from the ocean to the atmosphere, but in the overwhelming part of the oceans there is a flux from the atmosphere into the ocean, and carbon dioxide is fixed by the ocean and stored in the ocean. So the atmosphere is the result of the global carbon cycle. Everything in the end is integrated by the atmosphere, but there are several fluxes underlying these concentrations in the atmosphere, and these are of course the terrestrial ecosystems, these are the fossil fuel emissions, but it's also the ocean, and 70%, roughly 70% of the global surface is covered by oceans. It's an important part of the global carbon cycle, and I think it's still really underestimated, or let's say not underestimated, under observed. So the observational networks that we have on the oceans are too small, they are not really sustainable, and we need large investments into the ocean carbon observations during the next years or decades even. But we don't know exactly what are the uncertainties, what are the detailed drivers, and that's why we need a lot of these pCO2 measurements, that we can really get a global information on the ocean. And of course, these measurements have to be reliable, they have to be standardized, and it's important that the data can be compared to each other when they are coming from different technologies and sources. So what you are going to do in the next days is a really important work for the overall observations, but it's also a really important work for the single contributors to IOCCP, like ICOS, but many other research infrastructures or networks or institutions. So I know from my earlier career as a scientist that these kind of intercomparisons of methods of sensors is always a hard work and it's always tricky. So I wish you good luck in your endeavor to get good standardized observations, and I also wish that you have some good days among colleagues and have some fun while working on this intercomparison. I think you're doing a really important work for getting things standardized, getting things more sustainable. So again, good luck, welcome, and have a good time.
Thank you, Werner, for these kind words and for a great perspective. We will move to our second speaker. Our second speaker today is Richard Saunders. He is an ICOS OTC Director. He is also a senior scientist at NOC and honorary professor at the University of Southampton. So without further delay, Richard, the floor is yours.
So, hello everybody. It's a real great pleasure to be here speaking to you. I'm as was said, I'm from the ICOS Ocean Thematic Centre, which is based in Bergen in Norway. And Andrew Watson and I, Andy Watson, many of you know, is in Exeter, and we steward the Ocean Thematic Centre through its existence. So, could I have the next slide, please? So I thought it might just be worth telling you a little bit about what the Ocean Thematic Centre is and what it does and how it works. Werner gave a great introduction to the rationale for ICOS, why it exists, how it was set up, and what its purpose is. We're a component part of ICOS, and so ICOS consists of a head office in Helsinki led by Werner, a lot of observing systems that you can see in the map to the right-hand side of this slide, and then various thematic centres that exist to support the observing systems. So our strapline, our mission, is to help the ICOS ocean observing community deliver the data we need to quantify the ocean's role in planetary carbon cycling. And we have a whole series of activities that we undertake every year in support of the ocean stations. So firstly, we undertake a great deal of advocacy work. Nothing happens without money, and it's important to kind of support the stations in their ambitions and in their delivery of science and policy and data to end users. We have an activity we term labelling, helping the stations to document that they make the highest quality measurements consistent with international best practice. Because the raison d'etre, the rationale of ICOS is that we exist to support stations that deliver the really highest quality data over a very long time period so that changes can be observed. We have a work stream around data, building and sustaining the data pathway between shipper and the policymaker, training, helping the community of stations to deliver the highest quality data, and technology, exposing stations to the next generation technologies to allow them to make better, cheaper, faster, less power-intensive observations. And this task, this workshop, this pCO2 intercomparison, fits into a number of these work activities. And so I'll just say a few words about some of the others now. Can I have the next slide, Arthur? Okay, so this is just a brief word about our training and support program. So we support stations by supplying them with reference gases, by paying for their sensor calibrations. The ICOS network contains both membrane sensor based stations and showerhead equilibrator directly calibrated to gas standards observations. And we visit stations to support them in their work, in principle as often as required, in practice hardly at all in corona times. We also run a training program. So we have an annual workshop for the ICOS community on diverse subjects, sensors, data reduction, really whatever the stations feel they need most help with at that stage of their evolution. And then we contribute to summer schools. So we support the IOCCP summer school, we support the SOLAS summer school, and ICOS itself has a summer school, which again has been impacted by corona, as have so many things. Could I have the next slide, please? So one thing I wanted to pick out particularly, I imagine this will get mentioned later, but Steve Jones, who's in Ostend now, who will be known to many of you, leads work on a software package known as Quince, semi-automated data transfer from your ship to SOCAT, facilitated by the Ocean Thematic Centre. So that undertakes a range of activities. We calculate automatically carbon dioxide concentrations, quality control, publication of data automatically, online help and support, and really importantly, we maintain a record and an archive of all relevant parameters around the observations for sort of posterity. And you can see an example there of some data ingested into the Quince software and displayed. Can I have the next slide, please? So one of the things that we spend an awful lot of time doing is thinking through what an operational carbon uptake system will actually look like. Because I think it's important to recognise that the ICOS data sits at one end of a long chain that links it through to policymakers, and that chain of activities that we term the ocean carbon value chain is delivered by ICOS at one end, but by a whole number of other organisations along the value chain. And if that value chain is broken or one bit moves slowly, then there's a delay between our data, your data, the data that's acquired, ending up in a meaningful form so policymakers can make decisions on the behaviour of the ocean carbon cycle. So there's multiple steps along this: measuring the ocean carbon, quality controlling that data, blending with satellites, and then reporting to policymakers. And so I thought I'd just show you some thinking that we're doing at the moment around stabilising, improving, enhancing that ocean value chain. So can I have the next slide, please, Arthur? So this is a schematic that we've put together around where we are with the ocean carbon value chain. So at the bottom left, you can see its initiation, the components exist, they're science-driven, they're slightly ad hoc, and then gradually over time, money's invested, and we get to the point where we feel we are now, where there's individual components coupled together, but the system as a whole lacks coverage and resilience. And our perspective is that given the urgency of the climate crisis, given the susceptibility of the ocean carbon cycle to change, we need to be kind of sitting somewhere up to the top right-hand side of this diagram. Near real-time delivery of ocean carbon uptake estimates to UNFCCC, full global coverage, all components resilient, everybody working in the value chain knowing what they're doing, everybody in the value chain being salaried, which doesn't necessarily happen at the moment. So this diagram is something that we're thinking a lot about at the moment, And the pCO2 intercomparison sits very firmly into this. And so if I could just have the next slide, please. So this intercomparison exercise is integral to step one. So that's the first stage of the value chain, collecting and acquiring really high quality data. And that supports the databases that we all know, where data is archived and supported. But if we don't get the basic data gathering right, if we don't reference our systems well to trace gases, if we don't understand the performance of our instruments, then many of the other stages will be more difficult, more time consuming to deliver. So I'd just like to finish this brief overview of what we do and where this activity fits into our work program by saying that I'm really delighted that after a year's delay, we've been able to run this. We've been able to send some of the staff from Bergen to Ostend to deliver it. I'd like to thank Thanos and the group in Ostend for delivering the activity. And I'd like to wish you a really successful trip. And Vlad, it's great to see you there. And thanks very much for the efforts you're putting in.
Thank you, Richard. I think everyone is convinced about the importance of this intercomparison exercise. But I should also mention this is not the first intercomparison exercise that's happening. And to give us a bit of historical overview, our two next speakers will present the past intercomparison exercises. But before we go to Arne, I'd like to remind you to type your questions if you have any in the question box. We'll try to answer them diligently. So the next we'll hear from Arne Körtzinger. He is head of the Marine Biogeochemistry Research Unit at GEOMAR, Helmholtz Center for Ocean Research in Kiel, Germany. And he will talk about the beginnings of pCO2 intercomparison exercise, and particularly about the exercise that took place in 1995 on board Meteor. Take it away.
Thank you, Daria. Can you hear me and can you see my presentation?
Yes.
Very good. Okay, welcome and hi to everyone. It's my pleasure to report to you briefly on the 1996, actually it was, International at Sea Intercomparison of Underway pCO2 system, which took place on a cruise of the German research vessel Meteor across the Atlantic Ocean. Here we see a group picture just with the participants of the pCO2 intercomparison. You may spot a few famous people like back down in the front, Hisayuki Inoue, or Soma Ken Johnson in the back, Masao Ishii, Craig Neal hidden in the back. So I have to say this was not the first big such exercise. In fact, the mother of all pCO2 intercomparison exercise had occurred 2 years earlier. Upon invitation of Andrew Dixon to his lab at Scripps. And this is another historic picture. I'm realizing I've reached the age where people ask me to do historic perspective talks, which is an interesting observation, of course. Anyway, so this was the mother, so to speak, of all pCO2 intercomparisons. And again, a few familiar faces, Ray Weiss and David Ho and Andy Watson in his famous MOC t-shirt and so on. So that was the first such exercise that took place, and I happened to be one of the invitees, participated as part of my PhD project in this intercomparison with my just finished pCO2 system. And I think I got inspired at that intercomparison to do one at sea, because I thought doing this under the real conditions that you have on a vessel may still give slightly different results as compared to more ideal lab installations. And I had the very unique opportunity to secure some 16 free berths on an transatlantic crossing of the Meteor to invite people to this pCO2 intercomparison. It was the M36, first leg of the M36 cruise of Meteor from Hamilton, Bermuda to Las Palmas. And since there was a very, very small scientific program, it was more a transit cruise, I also had full control of the cruise track. So I made this big hook-like cruise track, because the idea was to encounter as large a temperature and salinity range as was possible. And that worked actually very well. This is the temperature and in black and blue and salinity recording from the thermosalinograph throughout the experiment. And you see that we actually covered a large temperature range from 6 to 25 degrees, which some very extreme temperature gradients where temperature changed almost when steaming by half a degree per minute, with a total step of 10 degrees or so of over 15 minutes or something like that. And also the salinity range was reasonably high. So these very steep changes, of course, in temperature, of course, challenged the pCO2 systems more than you would typically be able to mimic this in a lab. We thought a lot about providing the same conditions to all the systems. So rather than depending on the ship's own seawater pumping system, we installed a very large 350 liter per minute submersible pump, which was down in the bottom plate of the moon pool, so that all systems could be hooked up to exactly the same very large flow rate of water. We had a CTD installed right at the intake. Also, we had to provide different types of power. The Japanese world, where you have two different parts of the country which run at different hertz. Because of that, we even had to provide 115 volt and 60 hertz to at least one of the systems. So we wanted to provide the ideal and identical environment. In total, then we installed 7 underway pCO2 systems. That was as much as we could cram into one large lab on the Meteor, all hooked up to the same water flow. There was one discrete pCO2 system run by Craig Neal from Brookhaven. Ken Johnson brought his SOMA and operated, I think, for the first time also in underway mode. Ludger Mintrops, many of you will know, Ludger provided measurements from his winter system, and also a discrete pH system for Andrew Dixon participated. All systems had a common seawater supply, but also we provided, like it's done now, a common calibration gas supply. So I was able to purchase a suite of 12 brand new calibration gases from NOAA CMDL for the experiment. So all groups could have those that they needed for their calibration routines as calibration gases, and were asked to measure the others as unknowns, so that we had some checks on the performance of the calibration routines. And also those systems that were able to measure air were asked to run their sampling lines to the same spot on the Compass platform, so that they were all sampling the same kind of air at the same time. That was already quite a hassle to get all that on a ship. We had a number of types of equilibrators represented: showerhead, bubbler, and thin film equilibrators. Some were vented, some not. We had a large range of flow rates from 1 to 15 liters per minute of seawater flow rates, and also the airflow varied over quite a range. All instruments featured NDIR measurements, but some were measuring on dry and others on wet gas. And the number of gases needed for the calibration routines was kind of different. Some didn't use zero gas, some did. Also, a number of span gases varied, and also the equilibration time constant varied among the different of the pCO2 equilibrators over a range from 1 to 5 minutes. Some of the outcomes, very briefly, only there's a paper from 2000 where we summarized the outcome, a group publication from the entire experiment. The first and surprising outcome was that people were not paying attention to the calibration of their thermistors that they were using to measure the equilibration temperature and then correct back to in situ temperature. Offsets of up to half a degree were observed, and they would have introduced, if not corrected for, uncertainties or mismatches among the data, pCO2 data, of up to 7 microatmospheres. So without that exercise, we would actually have not a very good agreement throughout the experiment, and might have misinterpreted this as issues with the equilibration or the CO2 measurement. We learned that remember, this is 25 years ago. We know all that for sure now, but at that time we realized that the polynomial of the LICOR was not sufficiently robust to be just adjusted by the zero and span gas function, so by two simple gas measurements. So that was clearly an outcome. I think the blue, we won't be looking at this in detail, but the blue line here was an instrument that was calibrated at 350 and measured the others, the other gases as unknowns, and you see clearly this offsets positive and negative depending on to which side of your calibration or span gas the concentrations that were introduced by not really changing the polynomial adequately. So clearly the recommendation was you cannot go simply by one span gas. You need I think you need at least 3 calibration gases. Another outcome is that 6 of the 7 systems were able to measure air, and we did air measurements, and overall the agreement was pretty good. The summaries you see then on the bar graph on the left agreed very well with the atmospheric, the NOAA CMDL atmospheric station at Bermuda West and the Azores. But you see, if you look at the details, you see deviations, and they were actually more associated with the systems that were measuring on wet gas, because the wet gas measurements just loses a little bit of accuracy and also has transient issues if there's a strong temperature or moisture change. And also we observed that that if there is very cold temperature and there's no thermostating of the gas that is measured before entry into the NDIR cell, the cell temperature may actually be pushed away from its ideal cell temperature, and then you have temperature carryover effects in the NDIR measurements, which can easily be avoided by having some kind of a thermostating loop. And the most important part, of course, is looking at the pCO2 seawater data itself. And we did I did this at that time. I did a careful job at matching all them in time with a different time constant, and then make sure there's no mismatch in the timing, taking into account the different time constants of the data sets. So the outcome was that quite a few systems agreed to each other very well throughout the cruise after correcting for the temperature offsets most of them had. And this didn't depend on the dimension or design of the equilibrator. So very different equilibrators did in the end agree very well. So and actually, if well maintained and running well, a system that's generally carefully designed can actually do measurements that agree throughout the cruise to within 2 microatmosphere, and that was, I think, a very nice result. There were a few that were outliers. In some cases, we had issues where we identified malfunctional parts like water in the NDIR cell and things like that. But others, that's the red trace here, were of a very different concept, and clearly that concept didn't work so well. We can't go to the table really, but you see that like C and D and E, those 3 instruments agreed throughout this 10 or so 8-day experiment to within 1 or at least 2 microatmospheres, and others like B agreed most of the time, but then had issues during the periods where the water was very cold and this temperature carryover occurred into the NDIR cell. And then with this offsets system like the one with F, that clearly, due to the way it measures the pCO2, had an issue and caused really errors. So I think we were happy with the fact that agreement is achieved. And if you look at these cross boxes on the plots, both the discrete pCO2 measurement done by Greg Neal on I think 6 samples, discrete samples per sampling spot at a fixed temperature 25, agreed very well within a few overall, I think within less than 2 microatmospheres, and also the pCO2 calculated based on the CRM reference DIC and alkalinity measurements. I think they also did agree to within usually 2 microatmospheres. So we actually were quite happy with this overall agreement, giving us the feeling that yes, 25 years ago already very good pCO2 measurements could be made. So, I mean, I give you an insight how this lab looked, where all the instruments were crammed into one space, and we got the message back from the crew, which had seen a lot, that today this probably was the messiest ever look of the geology lab on the Meteor. The seawater was provided through overhead lines. Some of them were actually not totally tight at the fittings, so we had dripping water from above all the time, so we had to span little umbrella-like things. That's why we wrote about the floating dripstone cave in the US JGOV's news of that year. And also we got rid of the waters through floor drains, which during a few days with strong swell actually started a little bit to become a bit cloggy, so we had water leveling up at times from underneath. So it was a challenging experiment that usually is not the case on shore. So with that little scenery during a more quiescent moment of the exercise, I wish the group in Ostende all the best. I'm totally excited this is happening at this scale now. I wish you the best, and hope that people will write into your guest book something that they wrote into the GEOMAR, in the Meteor guest book, where they drew me as a totally stressed out and where a person in a maze of whatever line you're thinking of, water, gas, and so on. Thank you very much, and I look forward to any questions you might have. Thanks for your attention.
Thank you, Arne. Last time I seen Toby, he looked exactly like that, so don't worry.
See, yeah.
Okay, very good. I see the questions are coming, very good. We'll take questions after the next talk. The next speaker is Professor Christopher Sabine. He's Associate Dean for Research at the School of Ocean and Earth Science and Technology at the University of Hawaii at Manoa. And Chris will share a summary of the lesson learned from a couple of actually intercomparison exercises that he took an active part in. So please, Chris.
Hello, everyone. So can you hear me and see my screen?
Yeah, it's all good.
Excellent. Right. So I would like to continue on with the comparison exercises that were conducted over a couple of different years following Arne's experiment. And so the first one I'll talk about is this 2003 intercomparison exercise in Hazaki, Japan. This was put on by Yukihiro Nijiri from NIES, the National Institute of Environmental Studies. And it really was kind of modeled on Arne's excellent cruise comparison study that he just described here. And the idea was to build on that. So the findings of that exercise really were focused on the effects of, or the importance of measuring temperature and the calibration of the NDIR systems. The idea of this 2003 was, one, to try doing this comparison at a fixed site in coastal waters, but also to, in particular, look at the different equilibrator designs. And so there were 7 different systems on the Meteor cruise. In this exercise, there were quite a few more different systems representing a range of different approaches, from the shower heads to the bubbles to membrane filters to modified bubbling systems. We also had a couple of in situ systems that were not typically used on ships as underway systems, but like the Carioca system that's used, and the SAMI system that were used on moorings, and the Mbari mooring as well. One of the major findings of this work, however, was that there were some unique challenges associated with this coastal system. And so this is a plot showing, in this case, the difference between the Carioca system and the NIES system over time. So the x-axis is time, and the different colors here represent the pCO2 of the waters that were being measured. And so what they found was that there was a drift over time, or in the difference between the systems, and that that difference also was a function of the CO2 concentration. So you see these blue symbols were at the low CO2 values between 250 and 300 microatmospheres, and that offset was different from, say, the greens that were in the middle range of 300 to 400, or the reds that were 400 to 450. And all of that was changing, was drifting over time. So it became very complicated to really evaluate what the differences were. But one of the primary conclusions, and what they ended up discovering from this study, was that the high organic matter content in these coastal waters in Hazaki were causing trouble for some of the sensors, because the organic matter would get into these systems and it would start to decompose, and that would change the CO2 within the CO2 systems that were being measured. And so that gave a positive bias to some of the systems, and that bias was changing, was increasing over time. Despite that, there were a few conclusions, meaningful conclusions, that were discovered, kind of relating back to the findings of the Meteor cruise of the importance of measuring temperature. That was thought to be primarily in the warming, or the change of temperature between the seawater intake on the ship and the equilibrator. This took that another step farther in suggesting that the biases that could be introduced from temperature were also a function of the equilibrator size. So what they found was that large equilibrators had a smaller temperature change within the equilibrator itself, but some of the systems that had very small equilibrators, there was actually an important temperature correction that was needed for the warming or cooling that was within the equilibrator itself. They also found issues with the resupply of air that could give a positive bias in the low pCO2, or a negative bias in the high pCO2. So the equilibration efficiency and resupply was observed to be an important issue that needed to be addressed. Equilibrator pressurization and depressurization was also a major source of noise. So we had some equilibrators that were vented and others that were not vented, and this was identified as a particularly important issue that needed to be addressed. And then again, the membrane type equilibrators were found to have a bit of a memory effect, and that was particularly troublesome in these coastal waters, where this organic matter would get on the membrane and decompose and cause problems. So those were the findings of the 2003 experiment, and from that it was I forgot one. The last one was the difference of the equilibrator air and the standard gas temperatures that also introduced some uncertainties. Anyway, so after this 2003 experiment, Yukihiro decided he wanted to try this again, but with more controlled conditions and with a cleaner water supply that did not have all this organic matter. And so we had another comparison exercise in 2009 in Choshi, Japan. And in this case, we were using a very large indoor swimming pool, basically, that was filled with seawater. And in this one, we had 7 underway systems and 7 moored systems. We ran the experiment for 5 nights. And in this case, we were actually using sodium hydroxide or hydrochloric acid to adjust the pCO2 of the water in this tank so that we could, but once it was adjusted, then it was nice and stable so that we could do a really precise comparison of the different systems. So you see here that the changes, we started off on the first day with the pCO2 in the tank being around 280 parts per million. It was then adjusted up to 440, then down to 350. And then on the 4th and 5th days of the experiments, we were actually changing the systems as we were measuring them. So on the 4th day, we wanted to see what it looked like as we were increasing the pCO2 and measuring it across that increasing. And then the last day, we started with the high and brought the pCO2 back down. And so we were looking at the changes as we went from high to low. Here's a picture of it. I call it a swimming pool. It looked like a swimming pool, but actually it was a tank that we were allowed to use from their fisheries organization. It was this giant tank that where I guess they would put in schools of fish, and then they were this was typically used to test different nets. So they would drag different nets through this large pool and see how the fish were avoiding the nets so that they could build more efficient nets. Anyway, it was in this giant hangar. We were there in basically in the winter, so it was freezing inside this hangar, which did not have any temperature control. But anyway, these were the moored systems that were put in. There were a couple of SAMIs. I was running the MAP-CO2 system that we had started building there, which was shown as the second from the left. There was a large intake in the middle of the system for the underway systems, and then there were the jamstick buoys that were being tested there. We also had these large NIES systems that were actually in the buoys that were on the other side of this platform that was across the middle of the tank. These are the underway systems. So you can see on the left there was Kim Curry's system from New Zealand, and there were a couple of different general oceanics systems that were being tested. These are the NIES systems that were quite large and complicated and had different size bubbling equilibrators that they were testing on there. This is the NIES system, which was one of the predecessors to the GEO system, and was run by Kim Curry. Here's a PML system. This was one of the ones that did not have a vented equilibrator, which was discovered to be a problem, and so there were some challenges with that system during the whole experiment that were a problem. Anyway, so here are the findings from that 2009 comparison exercise. Under these highly controlled systems, we found that most of the systems were able to, were comparable within plus or minus about 2 ppm or less. Those that weren't within that 2 ppm, we were able to mostly determine what the issues were. For example, having a non-vented system was discovered to be a problem, and the vented equilibrators did a much better job. The moored systems were fairly new at that time, and so we were quite pleased with the results that suggested that generally the moored systems were within about 5 ppm of the underway systems, and it was observed that the moored systems at that time were kind of comparable in their results to what Arne had seen on the Meteor cruise with the underway systems at that time. But the underway systems were actually converging on a much tighter scale than had been seen in the previous comparison exercises. So then the last one that I'll cover is from an ACT, Alliance for Coastal Technology evaluation. In this case, they were specifically interested in comparing the various autonomous systems that were coming out around that time. The Alliance for Coastal Technology, coastal is in their name, so the idea too was to try and go back to the coastal system and see how these systems were performing in coastal waters. And one of the things with the ACT comparison exercises, so they do this with various sensors, salinity sensors, oxygen sensors, pH sensors. They've done a number of these different comparisons, but one of the kind of defining aspects of the ACT comparison is they don't actually directly compare or evaluate these systems. What they do is they put them all side by side, and they have a what they consider to be a gold standard system that provides what they consider to be the correct answer, and then they evaluate each of the systems relative to that gold standard, and they don't do any comparison of each of the sensors to each other. It's up to the community to do that. Anyway, it's a little bit different approach, but we did two primary comparison exercises. One was in Hood Canal in Washington State, and the other was in Kaneohe Bay. Again, two very different systems, two very different temperature regimes. We also talked about doing a comparison exercise in Venice and one in the Adriatic Sea. The Venice one did happen, but was only a couple of systems. So I'm not really going to talk about that. And I don't think the Adriatic Sea one happened. It might have, but anyway, I'm going to focus primarily on the Hood Canal and the Kaneohe Bay system. And in that case, we were comparing in both cases to discrete measurements and to the map CO2 buoys that we had in both of those cases, in both of those locations. And so some of the results that we had there were, again, because it was an ACT comparison exercise, there wasn't a direct comparison, but we found that there were significant challenges in the different equilibrator designs and in the response times of the different moored systems. So the SAMI CO2s, for example, had a much slower response time than some of the other systems, and particularly in these coastal waters, we were seeing very steep both time and space gradients in the CO2 systems. In the Hood Canal, we found that differences in the location of the sampling sites, they were all put on the same buoy, but they were perhaps as much as tens of centimeters apart, and the vertical gradients in the Hood Canal system were so strong that even in these tens of centimeters difference in the location of the intakes resulted in different CO2 values that were, we think, real and gave challenges in how to interpret this. In Kaneohe Bay, so there it was a spatial issue. In Kaneohe Bay, the temporal changes, so we were getting diurnal changes that were many hundreds of microatmospheres that exposed the challenges of the time scale of the differences. So again, the time of the measurement and the equilibration time both were challenges for comparing these different systems. So anyway, a summary of kind of all of the lesson learned from those 3 different experiments, I'll summarize here. One is that as with all experiments, the more things you can control, the more consistent your results will be. We found that the best comparison, the most easy to interpret, I guess, results were found with that 2009 experiment where we had this very controlled environment in the swimming pool, and the best results and the most easy to interpret results were, in that case, the field-based measurements, and particularly in the coastal waters, were very challenging to interpret the results. Just in general, trying to do comparison exercises in coastal waters were a real problem. In Hazaki, we had issues with organic matter contamination. In Hood Canal, we had issues with extreme spatial gradients, and in Kaneohe, we had issues with the large temporal gradients that presented challenges. So yeah, these, particularly in coastal waters, and each time it was something different, and who knows what's going to happen if you try again. In each of the cases, having a gold standard system that you take as the truth, and one of the real challenges with any sort of carbon comparison exercises, we've seen this in the alkalinity and the DIC comparisons too, that it's very difficult to know what really is the truth, and ultimately you just have to pick something. So with the 2 Japanese comparison exercises, we ended up taking the NIES systems as the truth, as the gold standards. In the ACT systems, we took the pCO2 as the gold standard. Of course, that means you can't really evaluate what that system that you're taking as the gold standard. We did in all of these exercises try and look at discrete samples as a way of evaluating the systems, but it just really was not possible. You need, if you're going to compare underway systems, you need an underway system that you're going to take as the truth, because the variability is just too large to really use discrete samples. The Choshi comparison required that all systems use the same standard gas. That was a big step up that we found was really critical, so that you're not worried about how is this system calibrated versus that system calibrated. If they're all using the same standard gases, then that was one way to eliminate that as a variable that we thought was very important. We did find that there were offsets that they're different under different conditions. So while the controlled environment of the pool was very important, was great for comparing the different systems, we felt it was important to do this at different CO2 concentrations. So we adjusted the CO2 in the tank, and that was critical. So you don't want to just do this evaluation at one CO2 concentration, that doing it under different conditions was important, and not just at the stable conditions, but also at the varying conditions. And the other final thing is just recommendation to measure everything possible. I think in every one of these comparison exercises, we discovered some other thing that we hadn't anticipated as being important for affecting the system. So just measure everything you can, and you'll have the best opportunity for trying to constrain what the issues are. And so I will stop there, and I'm happy to answer any questions that you might have.
Thanks, Chris. I think we're running a bit over time, so we'll leave the Q&A session at the end of the presentation. So we'll move to Toby Steinhoff, who is leading this year's intercomparison exercise, and he will give us an overview of the upcoming activities in Ostend. So we'll take questions after the end of Toby's presentation.
Okay, can you hear us? I think Arthur is changing our slides, right? Yeah. Okay, then let's start there. First of all, thank you to the audience. It's of course very sad that we can't really see you and don't have most of you here, but thank you for your interest in this intercomparison. And of course, we can't talk about any outcome, which we hopefully can do in 2 weeks, but we want to at least show you what we are planning to do. So the names you see here, this is the basic group who started organizing this intercomparison here in Ostend. And when you go to the next slide, please. Then you see, due to the circumstances, we increased this group by a number of people, and the people in bold and underlined, these are actually the people who are now here in Ostend and, so to say, running the show, but more to that later. Next slide, please. So I guess I don't really have to go into detail why we are doing it, but maybe why is ICOS doing it. As you have seen, ICOS is, at least ICOS Ocean, is a heterogeneous network from more of 20 stations. We have measurements on ship of opportunity lines. We have measurements on fixed ocean stations, which means we have a very huge variety of different instrumentation that is used. And of course, new sensors and instrumentation comes on the market and is being used in the ICOS network. And on top of that, as you all know, also new platforms, or with the new sensors, also new platforms become available, such as sail drones or sailing boats. And here, of course, the question is, if you look on the map, you see the network, the ocean network of ICOS, how comparable are actually the measurements we are doing within the ICOS network, which then, of course, translates, since ICOS is a European infrastructure, also into the bigger picture of SOCONET, how comparable are the measurements we are doing at our stations, on our ships, how comparable are they also on the global scale, here mentioning SOCONET, and we all of course, submit at the end our data to SOCART, or we would like to see our data in SOCART. And the benefit of SOCART is the quality control, high quality data. And again, so how can we make sure that we deliver high quality data? Next slide, please. Yeah, okay, so now I already took away the slides, and we can go to the next one, sorry. So we thought about some summary why we want to do that a little bit more. So of course we want to do it for the science, because at the end of the day, what we're aiming for, we want to quantify the uptake of the ocean of CO2, and for that we have to know how good we are actually measuring CO2 in the surface water. As ICOS as an infrastructure, of course, we also want to do a service for the observational community, because questions are, which instrument should I use? What instrument gives me what numbers? How good are the uncertainties? How much is the effort I have to put into there? So we want to give answers also to this question to the observational community in a well-documented way, and not only based on a, well, I have heard this and this instrument is working quite well. And last but not least, we also want to do it for the instrument manufacturers. So we really want to stimulate the interaction between the users, us, and the manufacturers to, at the end, build the best product that is possible for the purpose you want to use it. And therefore, we also want to have this rigorous testing. Next slide, please. I shortly want to a little bit go back to the history of this intercomparison. I also wasn't included from the beginning, but I was looking a little bit back in all the folders, and the intercomparison of this pCO2 information was a core task of the Norwegian ICOS funding for the first funding period. And the first documents I could find were from fall 2018, where just a draft sketch was drawn how the calibration activity, it was called at this time, can look like. And it was just a meeting of scientists from ICOS, or called North in Norway, and from the IMR in Norway. And then in the middle box, you see, these are, so say, the header of the minutes of the second meeting, where we still could count the meetings. It was already starting to form the group, which it is now. And so I would say this is somehow the first meeting where we really, from then on, we went straight forward until today, from May 2019. And on the bottom, you see somehow the header of the meeting from our last official meeting, which was end of May in 2021. So this year, so over 2 years, we planned and prepared this intercomparison, and in the meantime, you see we could win Craig Neal from CSIRO in Australia, which really, I mean, we all know that Craig has a lot of experience with this, and he was a big help. And also IOCCP joined, which also shows us the importance of this exercise. Next slide, please. No worries, I will not run through all the text, but just again, in 2018, the first planning meeting was done. In 2019, beginning of 2019, the plans became concrete, and we formulated a tentative date, which was the 24th of August until September 2020. And we started to run some tests here at the FLIT site. Even in the beginning of 2020, we started becoming real, requesting detailed information from the PIs of the instrument. And then Corona came into play. In the beginning, we were pretty optimistic that in the summertime this will be over. But at some point, we had to realize that it's not over in summer, at least not in summer 2020. And in July 2010, we postponed the whole intercomparison to 2021, hoping to then again have everyone on site. But here we were a little bit faster in thinking. Already in August, 1 month later, we realized that also 2021 might not work with having everyone on site, and we already started developing the plan B, which we are doing now, running the whole intercomparison with a core team of 4 to 5 people. So then in March this year, we made the final decision that we will run it with a core team. And even after that, it turned out that members of the core team can't even travel, even coming from Europe. So we reduced the number from 5 to 3, which I think then some people started to have sleepless nights. But luckily we could win 2 last-minute volunteers to help with the setting up and assist with the work on site. So thanks to Vlad and Emma, who spontaneously jumped in, and yeah, now we are here and doing it. Next slide, please. So we looked at some facilities where we want to perform this intercomparison. One option was a facility in St. Andrews in UK, also an outside pool, more than 600 cubic meters. Next slide, please. Another option was in Halifax, Canada. It was an inside pool, also more than 600 cubic meters. And then we looked at the next slide, at the Bliss in North End, 5 cubic meters, so it's not a typo. And this is what we were actually going for several reasons. We thought 5 cubic meter are good enough. We will have enough water to supply to the instrument. We will have enough space to throw instrument in the water. And it allows us to quickly control temperature and the pCO2. And as a nice side effect, Thanos, as the host, so to say, here in North End, so Blitz is also a member of ICOS, so somehow things came nicely together. Next slide, please. Just to show that we not just blindly followed the attempt of the smallest tank that we could find. So we did run some tests with the tank. We measured the temperature in the tank. We changed temperature, and this is just an example where we submerged 2 temperature sensors that were checked before, of course, that they're agreeing with each other. And we distributed those temperature sensors in the tank up and down and on the different sides. On the upper panel, you see the actual temperature between something like 14 and 20 degrees. And on the lower panel, you see the difference between these 2 temperature sensors. And you see in the time where we didn't change the temperatures, both temperature sensors agreed very, very well, which made us very confident that we can create a very homogeneous environment in this tank. Next slide, please. Here you see on the upper panel just also the temperature over several days in 2019, and on the lower panel you see actually the XCO2 data, because here we didn't want to go too far, of two pCO2 instruments that we deployed in or next to the tank. And we also aim for the same. We're using acid and base to change the pCO2 in the water, and the big jump you see on the 20th of October. There we added acid to increase the pCO2. We were aiming for something like 700 microatmosphere, and you see, I think we kind of did a good job in our calculations, so it turned out very well that we hit the 700. So after this test, we had the feeling we really have control over this tank facility, and we will go for that. Next one, please. So again, just to summarize that, so we were looking for a 2-week exercise, and here's already the actual date with a 1-week preparation phase where we are now. We wanted to have 30 to 40 PIs on site max. We wanted to build groups around each sensor so that they already talk to each other beforehand. And we wanted to have defined conditions for a successful deployment. We called it quick start guide. So we asked every group around the sensor to develop a quick start guide so that it's clear how to deploy a sensor without reading a 100-page manual. Of course, we can only focus on surface applications, but we plan to have different pCO2 levels, different temperatures, and the initial plan turned out, or it was the idea that we have enough expertise and time here and in North End to change and to adjust. Next slide, please. These are the slide changes. We increased the preparation phase to 10 days so that we have enough time to set everything up. We decreased the number to 5 people. And if we have enough expertise and time to change and adjust everything, I don't want to say no, but it's now at least limited. Next slide, please. So again, we will use this one tank. We will have a submersible pump in the tank feeding water to all the equilibrator-based systems. We have the submersible sensors sitting around the pump. We will have several temperature sensors distributed in the tank to observe the homogeneity. And we have reference gases. They're provided by the ICOS calibration lab and traceable to WMO. They're ranging from 0 to 800, and all systems, at least all systems that are using reference gases, are fed by the same gases. pCO2 range, we aim for 200 to 800 microatmospheres. Temperature range 5 to 30. 5, we are not sure if we can really go that far down, but if the weather stays like it is, we will definitely can do that. We just have to open the door. Temperature change of 5 degrees only take a few hours, just to show you how quickly we can actually change the system. And we will provide to everyone, or all the PIs, the tank water temperature, salinity, room temperature, and air pressure, so that everyone should have all information. Next slide, please. So we will publish the results with real instruments names. So we will not go for ABC because we want to have it as clear as possible, as transparent as possible, and also to give the community a little bit guidance in what instrument to choose for what application and how to operate them. As I said, we asked every group around one instrument to provide a quick start guide, which now came in very handy as we're just a small group who has to set up a lot of instruments. But the idea is really to, in the future, have those quick start guides with the instruments so that the user has the responsibility to follow this guide, and they can look into the manual for details. But if they follow this guide, they should be able to get measurements with this quality, and the companies has a responsibility to provide this quick start guide so that everyone can actually deploy the sensor successfully. Next slide, please. So this is very important for us, and we really want to emphasize that. So we don't do this to say which sensor or which instrument is good and which is bad. It's also not about winning a prize. We will not give a medal out. And most importantly, the whole thing is not a one-way road. If on the way we see that one sensor doesn't perform and we find out, I don't know, we just have to turn it upside down and it works better, we're happy to do that. So we really want to communicate with everyone, with the PIs and the companies to get the best out of the whole thing. So we really want the community and the manufacturers to work together to produce the best pCO2 measurement that an instrument can perform. And here now at the facility, we can do it in a defined way and under defined conditions. Next slide, please. So we divided the instruments into 3 groups. Somehow surface instruments to be deployed on buoys, surface vehicles. We have submersible instruments to be deployed on moorings. And we have underway systems to be deployed on soup lines or research vessels. Of course, there's a little bit of an overlap. We will have 28 instruments, and there are 19 different types. So some are double or triple. So we have 5 surface instruments, we have 9 submersible instruments, and 14 underway instruments here in the facility. All groups will have access to the raw data of their own instruments, and of course to the auxiliary data as soon as possible, so at least on a daily basis. And we will document what we are doing, some kind of a lab book using a Google Doc where every PI has a link to, and so you can a little bit follow what we did and what we did not do to your instrument. Next slide, please. So the plan, how we want to run that, we want to set the temperature, then adjust the pCO2 level to whatever we think is good, and then let the system run for at least 2 to 4 hours. So this is also up to discussion to the group that is then actually also virtually running the show. We know that the water will warm. Our experience so far is 0.2 degrees per hour, which is good enough to have a nice comparison. The warming depends, of course, on the pump in the water, on all the hoses to and from the underway instruments, maybe also to the warming of the submersible sensors and room temperature. The pump and the warming of the submersible sensors we can't really influence. For the rest, if this becomes too much, we have ideas how to prevent that. And then when we are fine with what we see, we can set a new pCO2 level or go to the next temperature step and keep on doing that. Next slide, please. So all data will be processed, or nearly all data will be processed using Quince, which is the OTC software, which was Steve developed, was talked about earlier. It's an online tool for data processing. It does some kind of automatic flagging, and the most important thing, it outputs a uniform data format, which makes it a little bit easier for us to compare the data on a daily basis. But we asked all PIs to also process their data with their own routines, so we can really compare that we do all the same. Next slide, please. So we will have daily meetings starting on Monday, 28th of June, again, 1:00 p.m. UTC, with all the PIs of the instruments. This will be organized at Zoom meetings. The people already got sent the links. There we will discuss what did we do in the last 24 hours, what was the response of the different instruments. We will have a general discussion about the findings and agree together what will be the next step of the plan for the next 24 hours. And after this meeting, we also will allow time to have meetings with individual PIs to maybe just discuss what, if there's an issue with their sensor, we are happy to talk in a small round what we can do to help to make it better or whatever. Okay, next slide, please. And now just a few pictures. So you saw maybe the tank before. This is a drawing. Here you see the one tank, the single tank standing there. This is the one we are using. We don't see the submersible sensors, but we put stages in so that we get high enough that all equilibrator-based system can flow back by gravity. And this is somehow how the room is looking right now. Here it looks very orderly because there are no gas lines or water lines. Next slide, please. And here just some impressions from our setup. You see the truckload full of pCO2 instruments. On the left-hand side, you see us setting up the stages, crawling on the floor. This is why you made your PhD in marine chemistry. The next slide, please. This was us trying to figure out how to distribute the water on the upper figure, and on the lower figure, how to distribute the gases. This was definitely a mind-blowing experience, but we managed. So next slide, please. And this is just some impressions. As I said, here it doesn't look as orderly anymore. Then we started putting up the hoses and the gas lines. In the upper right corner, you see, how did you call it? Conference of black boxes. So black pelly cases, and people discussing what to do next. Next slide, please. Yes, and here you see us as a team a little bit far away, but this is in front of the NIES facility here in Ostend. If you go to the next slide, please. This is us in the facility. So I just very unpolitely start on the upper left. So it's me there, then it's Steve, then in the middle there's Hannelo from here from FLIS, Thanos, Emma in the middle, Silke a little bit up, and all the way on the top is Flood. So this is the team we are working here with at your instruments. Next slide, please. Yeah, this is actually everything we wanted to say for now, and we're happy to take questions. Can't promise that we can answer them all. We'll try.
Thank you, Toby. Thank you. We actually have quite a lot of questions to many of today's speakers. So if the speakers and panelists can unmute themselves and turn their cameras on, maybe we can go one by one. So fresh off Toby's presentations, there's a couple of questions, and I will just try to group them in maybe one question. One was about who are the PIs and which specific instruments will be compared, and also how could you comment on the merits and drawbacks of keeping these systems anonymous versus being open, and what is the plan for the intercomparison?
Maybe I start with the last question. So we will name the instruments. There will be no secret about that, and we think this is the right way to go, and everyone agreed to do that. The first answer, we can name now all the instruments, but we explicitly left them out of the presentation because it might become too long. But they will be published.
29
instruments. That's 28 instruments, 19.
Is it both manufacturers and research groups?
It's a mix between manufacturers and research groups, but we tried hard to, if we got an instrument from a manufacturer, that we also got one instrument from a research group, so to ensure that we don't only get the golden sensor that always functions perfectly, but also some instruments that are really used in the field.
Very well. And one of the questions, actually a related one, was to Arne. It was a question about the performance of, shower head, bubble type, like bubbler or thin film equilibrators. And the question was, which equilibrators performed well in your intercomparison study on board Meteor?
Yes, we had 7 different equilibrators, and this is too few to make statistics really. But we could see that 3 of the systems were agreeing throughout the experiments to within 1 or 2 microatmospheres. And luckily, 2 of them were of contrasting dimension and type. So one with a small water flow rate and a thin film type, and one with a relatively large volume and water flow rate. And since those agreed throughout the cruise, we decided not necessarily these are our gold standard, but the average of the 2, which agreed very well with each other, was called the reference throughout the experiments, and to which we compared the others. And the fact that the agreement was so good with 3 of the instruments, or 3.5 most of the time, and there was no distinction to be made whether one type of equilibrator was better than another. Our bottom line was, from our experiments, we could not make a recommendation on versus whether shower versus bubble versus thin film type, because there was no clear sign of differences. The difference came from other things, how people treated their NDIR instruments or the measurement gas itself, and how they treated the temperature measurement equilibrator, but nothing we could say really with the statistics we had at hand about the design of the equilibrator itself or its dimension. The only thing we could see is that the warming in the equilibrator relative to the in situ temperature was of course correlated with the overall flow rate. So the ones that had a water flow rate that was relatively small suffered the largest temperature increase, but was still within 1 degree, actually for all systems, typically within 1 degree of warming.
It's very good. The question, I think that was answered in Toby's presentation, but I will just say it again. Will the ambient temperature vary as well, independent of the water temperature? This can be of interest for the underway systems. It's the temperature in the room versus temperature in the tank.
You mean okay, Toby.
Sorry.
Yeah, that's for Toby.
So we have the chance to vary the temperature in the room, and we might want to do that, especially to decrease any warming effects. So if we measure at cold temperatures in the water tank and have 25 degrees in the room, we might introduce an error that is unnecessary. And the temperature will be recorded and reported.
Okay, great. There is a comment to Arne and his colleagues saying that this intercomparison exercise was one of my best cruises I've ever participated. and what was more important, that it encouraged the strong synthesis of pCO2 data, which later realized in the SOCAT. So well done there. And there is one big comment from Andrew Dixon, and I will just try to tease out a couple of questions. So one of them was about the efforts to compare underway and autonomous systems. So I think also Toby addressed that in the presentation, that there will be all kinds of instruments represented in the intercomparison, both underway systems and submersible systems. So I will pass that. And then a question, which future large-scale inter-laboratory comparisons are needed in order for over the next decade, the decade of oceans, in order to better characterize the uncertainty in the large database of pCO2 data, besides the intercomparison exercises? I guess that's a question for everyone.
What's the biggest, probably Chris is the best.
I mean, okay, so that's an idea for the future plan. I would say we should scale up Arne's cruise to a year-long cruise from the Arctic to the Antarctic, and then we definitely have a long-term edgy comparison.
Not me.
No.
I've heard from Richard it's expensive, so maybe ICOS can help with that. There's a question, how good is good enough for shipboard underway pCO2 measurements? Can this be expressed as a standard deviation overall uncertainty?
Let's wait for the outcome of this one, I think, to see where we stand.
I mean, I think of course, we in summer always have these 2 microatmospheres hanging over our heads. But I would say maybe let's go one step back, because we're talking about 2 or 5 microatmospheres now, just thinking about so-called flags. But one reason why we're doing this exercise here is that we can't even always 100% surely say that we do it within 2 microatmospheres, that we do agree with it within 5 microatmospheres. And for me, this is the first step in the direction that we actually can maybe quantify an uncertainty in instruments that are commonly used. And then there's an important next step that needs to be done to answer the question, how good do we have to measure? Is it maybe good enough to have 2 lines with a high precise 2 microatmosphere instrumentation on board, and in between 20 lines with a very not so expensive and extensive instrument with 5 microatmospheres, like sailboats or whatever? Maybe somewhere there we have to go. But again, to answer the question, I don't have a real answer, but I would like to answer, how good are we actually at the moment?
Very good. Another question also from Andrew Dixon about the gold standards and about the problem of getting gold standard for pCO2 measurements, and also having the laboratories being able to use this gold standard, similar to, I guess, the CRM material is used for total alkalinity and DAC. How this lack of standard can be overcome in the future, you think?
Can we answer this question in 2 weeks' time?
Yes. Well, we also don't as a group, we understand the importance of having a gold standard. It's critically important to have something like that. However, it will back up the fact that the gold standard will not be able to be evaluated, as Chris said. And we want to try to avoid that, because even that system that we consider as a standard, it might need some improvement, in a tweak. that might go from 2 to 1. Why not achieve 1 if it's necessary? So I think it's a fundamental question for the whole marine carbon community, how to define this golden standard. Even if I remember one time I've met Andrew Dixon a few years ago, Sweden. He also was not happy using his CRM as the calibration. It's a CRM, it's not a calibrant, and we're all using it as a calibrant. So but it's the one thing that we can use, and the only thing that we can use. How to resolve this conundrum? I don't have the experience or the capacity at the moment. Maybe we will have this bunch a statistical presence, and the statistics behind the many centers that we have might be able to give us a more coherent answer.
Thank you, Tanis. I think we're a bit over time, but there is a couple of questions left, but I think one more, and we'll leave the next. I'll save the questions, so maybe we'll ask them at our next webinar on July 12th. But there is a question about the commercially available pCO2 instruments that emerged over the last couple of decades. Can I guess Toby or someone comment on how much progress has been made since the early days of intercomparison, when it was mainly lab built equilibrators versus nowadays, where I guess many of them are commercially available. Or maybe Arne can also comment on
that. To be honest, I cannot give a straight answer to the question. I mean, but I think maybe turn it around. This is one of the motivation again why we are doing that, because we see all the technologies coming up. I mean, there are now handles there at the size of the shoebox. I put water in, I get water out. I put in a power and data cable, and then I get pCO2 data, which also maybe can lead to that people believe, oh, that's that easy to measure pCO2. So I think the answer is somewhere in between. It is easy to get numbers out of things like this, but still they need some care and some love to produce good results. And I think this is what we want to demonstrate here.
Again, we hope that we will be able to answer that question more, have a better educated answer on that question in 2 weeks' time. Saying that, we've realized that the suppliers themselves have made a lot of progress over the last decades. They have progressed. That's undoubtedly the fact. But the devil is in the detail, and this is the detail that we would like to try to find out and resolve, and make the users understand what sort of sensors they're buying for the application that they want. That's one of the aims of the exercise, as Tobias has mentioned, and as the group, that's one of the first things that we decided as a group.
If I may say something, add something, I think running these instruments over large ranges in pCO2 and temperature is useful, because there are these more anecdotic style comparisons between one underway system at sea and one sensor, and some of them look very favorable, these comparisons, and in other occasions they didn't look so favorable. I mean, you never know what's the reason, or does it depend on the pCO2 range, on the temperature range during that comparison. So I think spanning a wide range in pCO2 and temperature doing such an experiment allows you to test the sensors, the comparisons over a matrix of ranges, which is useful, and based on the outcomes, you have sometimes an idea of how to define best practices for each and every sensor that tries to accommodate the findings that you have with this systematic approach. And that's one hope I have, is really that a lot of things are learned from these comparisons, that they can be put into best practices routines that allow you to push always, depending, regardless of the exact finding, the different conditions you might have, pCO2 and temperature-wise, you still achieve the best possible agreement with references, as you know, have embedded into your best practices some of the shortcomings that were observed during these systematic tests. I think that will be a big achievement.
Okay, thanks everyone for your questions. Thanks audience for the questions, and thanks the panelists for answering them, or at least trying to answer them. I hope we'll have more to come in 2 weeks with the first results of the intercomparison exercise. Just to remind you, July 12th, the same place, the same time, we'll meet again and hopefully see what we got from this year's ICOS OTC pCO2 intercomparison. So again, thanks everyone for attending today's webinar, and hope to see you in 2 weeks.
Thank you very much.
Thank you very much. Just a closing thanks to OTC and ICOS for supporting, hosting things in Blizz, and the community for trusting us as well. Thank you very much.
Thank you. Bye-bye.
Thank you.
Bye-bye.
Thank you. Bye-bye.